Okay, this is question 2, and look, it's the 6-mark QER. So what does that mean? Remember that QER stands for quality of extended response, and in terms of us going into a question in an exam and responding to that question, what it means for us is, unlike a normal question where if I had a question that said describe and explain, and it was worth, say, 3 marks, then what I would have to think about is that I need to make 3 points because there will be 1 mark per point made. That is no longer the case once it's a QER question. The way that QER questions is marked is different, and we basically have 3 bands, a top, mid, and bottom band. And the way that those work is that the top band is 5 to 6 marks, the middle band is 3 to 4, the lower band is 1 to 2. And what decides which band you're in is essentially the quality of the physics in your answer. What decides whether you're at the top or the bottom of your band is the QER aspect, quality of extended response. So that's like, is your answer in a logical structure, those types of things. So it's worth having a careful think about that, really. As you can kind of see, it's the physics in the answer that's the more important thing to get right. If we're in the top band, the QER decides whether we get 5 or 6. If we have a really well written, well crafted response, but the physics is wrong, we're in the bottom band, and the QER is deciding that we get 2 marks rather than 1 mark, which is less significant. As a general rule, I normally advocate bullet pointing these because I find if you bullet point your answer, it's more likely to focus you. It's more likely that you will get the physics correct and not kind of get carried away with waffling. Often when you're marking students' works, students' responses to 6-mark QER, they spend lines of writing essentially saying nothing. There's an awful lot of extra wordage that doesn't really gain them any credit, and that's to be avoided because, you know, your time is short. 6 marks means that you'll have about 7 minutes worth of exam time to answer this question. If you're writing, you know, if a third of your page is filled with lines that don't gain you any credit, that is not a good return on investment. So with that said, how do we answer this particular question? We are presented with an IV graph, current against potential difference, for the filament of a lamp. Describe and explain in detail. Now notice it's describe and explain. So there's 2 aspects to this. In detail, the shape of the graph referring to the motion of free electrons. So we basically need to explain what's going on in this graph. So let me talk to you briefly about that. First things first, current is the flow of charge. It's the rate of flow of charge. And in something like a filament, that charge is carried by free electrons. So the first thing we're going to want to open with is some sort of reference to the idea that it is the motion of free electrons, the drift velocity of those free electrons, that is the current in a filament. Notice that this, up to about here, in this first section of the graph, the line is straight, and what that means is that the ratio of V to I is constant, and therefore resistance is constant. Be careful. The gradient of this graph is not resistance. That is a really common kind of mistake that students make. Here we've got V against I. Everybody knows that V equals IR. Therefore, I could write that that is true. So people tend to interpret that as meaning that the gradient of a graph like this is 1 over the resistance, and it's simply not true. What that means is that if I choose a point here, for example, the resistance at this point is the ratio of I to V. So if you like, that would be the gradient of this line, the straight line from the origin to that point. That is not the same thing as the gradient here. It is not the same thing. Sorry, 1 over in this particular graph. So be careful, do not refer to the resistance as the gradient of the graph. However, If this graph has a constant gradient, if it's straight here, that implies that the ratio of V to I is constant and the resistance is constant. As we can see further up here, that is no longer the case. So we're going to have to be able to explain why that is. I would suggest the approach to that should be to talk about the cause of resistance. So what is it that causes resistance? It tends to be collisions or interactions between those drifting free electrons and the ions within the filament. So that's where the resistance comes from. The next and arguably final phase of answering this question would then be to try and explain why that value has changed. Why is resistance changing? And specifically, why is that happening at higher values of I? And hopefully that is, you know, the explanation for that is something you're probably familiar with, even from GCSE. It's the idea that at these higher currents, if you think the power output is I squared, V times I. The power output of the filament is VI. So as we head up this graph, that is increasing, therefore the temperature of the filament is increasing. Well, what does that do? It increases the rate of vibration of the metal ions. It increases the mean speed of the electrons. It causes more collisions per second between the free electrons and those ions, and therefore a quicker rate of energy loss, which translates to a higher value of resistance. And that, I feel, would be a pretty complete answer for this question. So what's that going to look like? I've probably talked about it for long enough. Describe and explain in detail the shape of the graph referring to the motion of free electrons. So I would suggest the first thing we need to say is that current is flow of charge in the filament. That charge is carried by free electrons. Oh, that's not how you spell carried. Carried or transferred. Something along those lines. So how do we link that to V and I? Potential difference, let's start with the potential difference. Causes a force on free electrons. You know, at one end of our filament we've got positive, and at the other end we've got negative. The negative end of the filament is repelling those electrons. The positive end is attracting those free electrons. So it causes a force on free electrons, which gives them some sort of drift velocity or non-zero mean velocity. The electrons themselves lose energy in collision with metal ions. So far, really, all I've done is explain what current is, what potential difference has to do with it, and I'm kind of basically now describing resistance. Oh, this is cause of resistance. Then, you know, we have to really mention that resistance is given by V over I. By Ohm's law. And these are all statements that are general, to do with current more generally, to do with sort of any flow of standard current. So let's talk about this graph. Initial gradient constant. Which implies V over I constant. So R constant. Okay. Then at higher V, and I will mention the power output since P is equal to VI. The temperature of the filament increases. That in turn causes ions to vibrate faster. And free electrons move more quickly. It's worth remembering that that higher temperature doesn't affect the drift velocity, but it does affect the speed that electrons are moving at. So in general in a metal, electrons move very, very quickly indeed. The drift velocity is very small in comparison to the random motion of the electrons. Those two factors imply more collisions per second. Between electrons and ions. That in turn implies a higher rate of energy loss. For the electrons. Which in turn implies higher resistance. So that ratio of V over to I changes. And that's causing our graph to level out. Maybe levels isn't quite the best word, but you know what I'm trying to say. I just haven't thought of quite the right words for it. Hence the graph levels out. I'll go with that anyway. Maybe I'll just explain what I mean by that. So what I need is larger increase in V required for some increase in I. I think that's it. I think that's pretty comprehensive. Did that take 7 minutes? I don't know. So if I can just go back briefly to what I mentioned here, our goal is to get top band. I may not get 6 marks because I've done this in bullet points. Now, with that said, I would kind of argue that this is a logically laid out answer. So I think it does flow reasonably. I think the logic flows reasonably. However, whether you get 6 marks for that is debatable. It is a QER mark after all. But does my answer get me into the top band? I would be pretty confident it does. Where we end up band-wise depends on the physics, and that's pretty comprehensive here. I've mentioned all of the relevant details. I've defined current. I've talked about the definition of resistance. I've talked about where resistance comes from. I've referenced that to the graph. I've talked about why the graph changes shape in terms of the temperature of the filament increasing. I've talked about why the temperature of the filament increases. So I think this definitely gets into the top band, and that should be your goal in these. Getting the QER mark is, I feel anyway, secondary. If you think you have enough time in an exam, then by all means bullet point your answer on the back page in the spare paper, and then feel free to, if you have time, to come back and convert your bullet pointed answer into something that's written in prose that is going to definitely secure that QER mark. But for me, I think the more important thing is getting the physics on the page, and if that means doing it in bullet points, then I think that is the way to go. One of the options you've got, you could always, this is question 2a, you could always put your star here, extra paper, and bullet point your answer on the extra paper, and then if you have time, you can come back and start writing it in, at the end of the exam. If you find you've got the time, you could come back to this question, you could start writing it in full kind of sentences, aiming for that QER mark. If you don't have time to do it, you've still got the physics answer that's going to get you 5 marks. It's there, you've written down the physics. So that might be a useful approach for that type of question. Okay, I've spent far too long on that. Let's move on. Here is a question being used to determine EMF and internal resistance R of a cell. We're going to be adjusting this variable resistor. A series of current and PD readings are taken and plotted as shown. So remember, with a circuit like this, as we adjust the resistance here, we get different amount of current flowing. We're measuring the potential difference. This is the terminal PD, the PD we measure outside the cell. That is actually going to decrease as the current increases, because as time goes on, the PD drop across this internal resistance is equal to I times R. That increases with I, and V here that we're measuring is the sum of the EMF produced by the cell minus the potential difference drop across that internal resistance. So determine the EMF and the internal resistance of the cell. Uncertainties are not required. So have a look. I'll just write the equation again here. EMF minus I times R is equal to V. I want this to become a straight line graph. So if I write that in this form, V is equal to minus R times I plus EMF. We can sort of relate that directly to a straight line equation where V is Y, I is our X variable, the gradient of our graph is minus R, and the intercept of our graph is the EMF. So what we need then is a straight line through these points. Let me just whip out the ruler. Where do I get the ruler from? There it is. And I'll try my best. This is always a little bit fiddly using a kind of online version. So, line of best fit, as a general rule, you want a roughly even number of points above and below the line. There's no error bars here. It's actually quite a lot easier with just a ruler in your hand. But something around there I'm going to go with. Let's just draw my line. And I'll get rid of this ruler. So what I would say is, anytime you're getting information from a graph and you've drawn a line, it is very sensible to make it very clear on the graph where the points are that you've taken your gradient from. So here is a useful point, and again, always use points that are well spaced apart. Don't take a gradient across sort of here. There's no need for that. So don't do it. Choose a nice big triangle that you can get a gradient from. So I'm going to go with here. Oh, I was really hoping that OneNote was going to... No, I've moved my line. I was really hoping that OneNote was going to turn my line into a straight line for me then. Oh, what is happening? OneNote, please make it stop. I want to scribble. Yeah, hopefully I haven't moved it very much. So yeah, I would draw on the triangle that you use for the gradient, and I would label that up with, in this case, I've got delta current down here, or if you prefer, just delta x, because it is going to be a gradient that we're going to find. Always be careful with the units. This is amps, you know, but it's always worth checking that the units in the scale are the units that you think they are. And be careful reading the scale as well. So this is 0.3, and these minor divisions are 0.02. So this is at, you only need to read it to the nearest whole division. You don't have to start thinking about, you know, how far between two minor divisions is it. There's just no requirement to do that. So that's 0.34, this is 1, so the change is therefore 0.66 amps. And delta y, we've got 1.2 and 0.7. So a change of 0.5 volts. The intercept here, this is 1.4243, oh sorry, 424446. At that intercept, again, to the nearest minor grid line is fine. I don't need to be worrying about that. I don't need to be suggesting that that's halfway between two. So that is all of the information I need. You know, there's 4 marks for this. So probably not a crazy idea to make it obvious where you're getting your numbers from. So V equals EMF minus IR. So I'd already written this up top. I'm not sure why I didn't put it down here. And just make it really clear that you know what is happening here. So gradient of our graph then, changing y over changing x, 0.5 over 0.66. And as I say, that's why it's so important to just check that you have got the the units correct. These are volts and amps, no milliamps, no millivolts or anything like that. Delta y is actually minus 0.5. And that equals minus r. Therefore, r is equal to 0.76. And those are ohms because I did check my units. So that's r. And then the EMF is simply the intercept, and we can read that directly. We don't have to do any calculations. That is 1.46 volts. Done. Final part then. As part of the experimental write-up, Megan makes the following statement: readings of VNI will be taken quickly with the switch closed. I will ensure the switch is open between readings. State the importance of this technique when carrying out this experiment. So let's have a look at the experimental setup here. Yeah, there's a few things that we could mention here. We want the temperature of our cell to stay constant. If we were to, you know, especially since some of these readings at the higher end, we've got 1.2 amps flowing with a fairly low value on this variable resistor. So at those low values of resistance here, we'd have quite a high current flowing and the battery could become hot. You know, if you think the internal resistance at 0.76 ohms, so the power dissipated through that is going to be the current multiplied by that. So, you know, that's a reasonable amount of power being dissipated in a small cell. So it's going to get hot, which will A, affect the experiment, and B, could potentially be a safety hazard as well. So that's all we need to say here. State the importance. Yeah, so cell may become hot when current high. which could affect the value of R and could be a safety hazard. Job done.